This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Your code is powerful, and so are you. And when you consider the reach of your code, it's clear that to deliver quality code, you must also deliver secure code. Where can you start? A first step is educating yourself on basic secure coding principles and beginning to put these principles into practice every day. Vericode's Secure Coding Toolkit is your go-to resource for all your secure coding needs. The benefits of our toolkit include learning best practices for secure coding, understanding how to secure your DevOps environments, learning to combat the most common software vulnerabilities. Stay secure and download this valuable asset today at www.vericode.com/SERadio.
This is Robert Blumen, editor of Software Engineering Radio. If you're hearing this, that means you're a listener of the show. But have you ever thought about being a host? It's a great way to talk to some of the most interesting people in the industry and get 30 to 40,000 people to hear your thoughts. Contact us, team@se-radio.net for more information.
Hi, this is Jeremy Jung for Software Engineering Radio. Today I'll be speaking with Aaron Patterson. Aaron is on both the Ruby and Rails core teams and currently works at GitHub. Aaron, welcome to Software Engineering Radio.
Oh, thank you.
First, for people who aren't familiar with Ruby, why should they check it out? What's good about Ruby?
Well, there's a lot of good things about Ruby. The reason I really enjoy Ruby is it's just super fun to program it with. Like, it's a really enjoyable language to use. But I think part of the reason it's a joy to use is essentially the consistency of the language. So in Ruby, everything is an object. You can contrast that with, say, Java, for example, that has objects but also primitive types, whereas in Ruby, everything is an object. So you only have to think about that one. Like the mental overhead is a little bit lower, right? So I don't know. That's why I enjoy programming with Ruby. It's easy to understand. So it's easy to understand and fun to use.
I see. So instead of having primitive types like Java, such as Boolean and floats that have different rules than normal objects, everything in Ruby is treated the same. So you can call the same base methods.
Yep, you can call methods, yes, everything. And it's really everything. Like classes are objects, modules are objects, everything's an object. So it's just really, I think that consistency, like I said, it helps to like lower the mental overhead of using the language. So you know what to expect. You're like, what is this thing? You figure out what it is. Okay, now I can just call methods on it.
I think that's one of the things that sort of, I think, strikes a lot of people when they start, I guess specifically with Rails, which is the web framework for Ruby. Mm-hmm. There's the example of being able to use like a number, like say 5, and then to be able to do .days.
Yes.
That's kind of the canonical example of people seeing that and going like, well, how does that work, right?
Yeah.
So I guess that's basically because 5 is a object and you're able to add.
You can add methods to it. Yeah. So the numbers have classes, and I mean the number 5 is just an instance of a I think numeric is a class, and you can just one thing you can do in Ruby that's I think unique to the language is that you can just add methods to classes if you want to.
Right.
I guess it's a good and bad thing. You can just add you can add methods to any classes you want to. So if you that people can abuse that,
right.
So don't abuse it. But that's a good example. So you can just add like the method days to the numeric class, and then be like 5.days. So I think one of the other defining characteristics of Ruby programming is the ability to do metaprogramming, which is essentially just programs that write programs, right? So you could kind of think of it as, I guess it's like code generation, basically. You write a program that will generate code and it evaluates it, and that's how you get a lot of the stuff in Rails. Like, for example, in your active record models, when you say like has many, whatever, you're setting up that relationship, it's actually a meta-programmed method.
Active record being the object relational mapper for Rails.
For Rails, yes.
And you're saying behind that single line of code, there's actually a ton of code being generated.
Yes. And then actually a more simple example is that's not Rails specific is if you write a class and you want to add getter and setter methods to the class, you just do like adder, accessor, foo, and that adds getter and setter methods for you. And it's under the hood, it's really just doing metaprogramming. It's defining a method that returns the value, and then it's defining another method that lets you set the value.
In Java, for example, if you have a class and you create for a person, you could have like a set name and a get name, you have to write those functions.
Yes.
But in Ruby, if you had a person class, at the top of the class, you could write adder, accessor, and that would generate methods on the person class
for you, yes.
For you to set the name and get the name.
Yep, exactly, yeah.
Cool. Next, I want to talk about a little bit about how Ruby is interpreted. So what does it mean for a language to be interpreted versus compiled?
So Ruby 1.8, well, before Ruby 1.9, Ruby was an interpreted language, and essentially what that means is that it would parse your code and it would turn the code into an AST. Before Ruby 1.9, Ruby would build an AST, which is essentially a tree data structure, and then the interpreter would walk the tree data structure, executing whatever was at that node in the tree would execute that particular command. So if you had a plus node, it would add the leaves or the child nodes of the plus node. So, and it would just do this for the entire parse tree of your program. And then in 1.9, it changed. Ruby got a virtual machine. And the main difference there is that the Ruby program is compiled into bytecode. And then the virtual machine executes the bytecode rather than walking a tree data structure.
And then, so when you say we got a virtual machine, right? So does that mean that the interpreter we had before is not considered a virtual machine?
I mean, I guess you could call it a virtual machine in that it's interpreting a tree, but I think the difference is that the interpreter is before 1.9, that particular style is essentially walking a tree and interpreting whatever instruction is at that point in the tree, whereas the virtual machine is really trying to model an actual machine, like it's a stack-based machine. So you generate instructions, and then this machine executes the instructions for it, as you would your C compiler generates instructions for your CPU, something more similar to that.
So the distinction, I guess, when you call something a virtual machine is that it's running commands sequentially, and there's a stack.
Yes.
That is pulling each instruction from.
Yep.
Okay.
Yep. Yes.
Whereas if it's from a tree or it's parsing a tree, then we don't call that a virtual machine, I guess.
I guess not. Yeah. I mean, it's not real. It's virtual.
Yeah, everything's virtual.
Yes, exactly.
So what language was the Ruby interpreter written in?
It's written in C.
Okay.
Yeah. So the interpreter is written in C, and also the virtual machine is also written in C as well. Yeah.
Okay. Why is C a good language for a virtual machine?
Is it?
I don't know. Hopefully it was, right?
I think that's an interesting question to ask. I don't know if it's good or not, but you can do tricks with C that you can't do with other languages, or would be difficult to do with other languages. So, for example, one of the techniques that the virtual machine uses is a technique called direct threading.
Okay.
Where it essentially emits jump instructions rather than typically what you would do in a virtual machine is you have a loop that pops instructions off and then
off of the stack.
And then just goes through your instruction sequences, looking at the instruction sequence, looking that instruction up in a table, and then jumping to the appropriate function for that.
Okay.
Whereas with a direct threading technique, you essentially eliminate that jump table and insert these jump instructions, like the offset of the function that you actually want to go to. So rather than doing the lookup in a table, you emit a jump instruction to say go, and I mean a machine jump instruction, not a Ruby VM jump instruction. You say go to this address and execute the code there, and type of trick is something that you can do in C that maybe you can't do in other languages. It may be possible, but it's a common trick in C.
So you said like you would normally have this lookup table that tells you, is that where in memory? Is that like in the stack or is that in the heap?
It's going to be, well, that lookup table is going to be in the heap, and essentially what it is just the key is the instruction, like say the instruction for the virtual machine. Say you have like a push instruction or something, and it looks that up in the table, and then it says, okay, well, here's the function pointer to execute the push instruction, and then it goes and executes that. Whereas using this direct threading technique, you can eliminate that lookup essentially.
So like you're going through a list of instructions, I guess, and you get to some kind of, I guess, machine level instruction you need to execute.
Yes.
And instead of looking at a lookup table in the heap, you would have like an offset, a memory offset. Just, I guess, would that be in the stack? Or
yes.
Okay.
Yeah,
and then
you'd say go there.
Okay, so right from the stack, you would say like, okay, go to this position from where you are.
Yep.
And you don't need to do the lookup.
You don't need to do the lookup.
Okay.
Exactly. Yeah.
Okay. And were you going to say something?
Oh, those types of like memory techniques are things that you can do. Like that's a thing you can do in C, where I don't think you could do that in Java, for example. Maybe you could do it in Rust, but I doubt it would be considered safe, right? So those types of unsafe tricks are things you can do in C.
But those are kind of, I guess, the reasons why you would use C, but at the same time, that's also why you're saying C might be...
It's dangerous.
Dangerous, yeah.
Yes, exactly.
Okay. So it's kind of like, it's a really powerful tool, and that's why everyone chooses to use it.
But it's a double-edged sword. Yes. But it's, and then the downsides, of course, are that C is not a very friendly language to use.
Yeah. Especially considered, compared to like Ruby or Python or other scripting languages.
Yeah. It's not like C does not spark joy.
You were saying, though, that, like, is C a good language for VM? And, you're kind of like, well, it is, and maybe it isn't.
Yeah.
Are there any, alternatives, like realistic alternatives, or?
Wow, that's a really good question. I have not thought of an answer to that. I would say, like, from my perspective, the two things come to the top of my head. First would be Rust. The second would actually be Scheme.
Oh, okay. Yeah.
Specifically, my favorite scheme, which is Chicken Scheme, but Chicken Scheme essentially compiles down to C.
Oh, okay. So in the end, you can't escape C.
Yeah, you can't escape it there, anyways.
Yeah.
But at least you can write in Scheme and not in C. So there's that.
So is it writing the scheme code is a safer environment, or what? I guess why would you say that?
Well, writing the scheme code. I guess I don't know if you could do the that direct threading technique that I was talking about. I don't know if you could do that in pure, just plain old Scheme. Scheme is a lot nicer to write than C is, and I think Rust is also a lot nicer to write than C is. So basically, when I think about it, I think about developer ergonomics, like how hard is the language to use, basically.
What do you think is like the main thing blocking, say, Rust from becoming a language that you could write VMs in? Honestly,
I don't think that there is anything blocking it necessarily. I'm quite sure people are writing virtual machines with Rust now.
Yeah, I know there's one for Python that a couple of people are working on. Outside of that, I guess right now it's a bunch of sort of toy projects, where people are trying to figure out like what is the limits of Rust, and hopefully, they'll find out like, hey, maybe this is something we could use in place of C, or maybe we still have a ways to go. Yeah.
So I personally don't think there's any blockers necessarily, because I think that those toy projects will eventually turn into real things. So mainly the blocker I'm doing air quotes for your listeners here. The main blocker I think is just popularity, like getting more people to use it. So
right.
That's the only thing.
So just adoption.
Yeah, exactly.
Yeah, I mean, it'll be interesting to see, like, in a few years, if maybe when somebody's thinking of making a new language, maybe they do look to Rust before they look to C.
Yeah, I personally would.
Yeah. If you were writing Aaron's Ruby VM or something,
I
like
would
maybe
probably go with Rust.
Okay.
Yeah.
Okay.
Like, I think mainly, I'd say probably the reason Ruby is written in C is essentially just legacy. Like, it's been around for 25 years. Rust has not been around that long, right?
Yeah. I mean, who knows? Maybe if Matt's the creator of Ruby, maybe if he was making it and Rust was around, maybe he would have chosen it.
Yes, yeah, it could be. And I think one thing I know we're talking about Ruby today, but one thing I like about Rust that I think is cool is you can write stuff in Rust and you can export symbols to C from Rust.
Oh, okay.
So it seems possible that, like, for example, I could rewrite Ruby's garbage collector in Rust, but still be able to embed it within a C project, as long as I exported C project such as Ruby, as long as I exported the right symbols. So I think that's one thing that's exciting about that language.
And for those who aren't familiar with C, when you're exporting a symbol, like, what does that mean in the context of C?
It just means that your C program knows, or the linker knows, where the function offsets are. So you can link against it and say, like, when you compile your C program, you're like, there's a function in this shared library and I want to call that function, and it's able to link and look it up.
Okay, so you could be in your C program, like because the Ruby VM is written in C.
Yeah.
And like you were saying, you could have calls to a garbage collector that's written in Rust, and you could call those directly from C.
Yes.
Okay, and it would have access to the actual, like, exact memory locations of those calls.
Yes.
Okay.
Yep.
Got it. So starting with Ruby 1.9, you said you introduced, or
Koichi, yeah. Koichi wrote a virtual machine, and introduced it.
Koichi, when he decided to create the VM, was there a specific reason? Was it like performance, or what was the primary motivator?
I mean, the main thing was for performance, but I know he also did it for his PhD thesis.
Oh, okay, yeah.
So that was probably another motivating factor. But I mean, really performance.
How much of a difference are we talking, I guess, between, the interpreter versus the compilation in VM?
To be honest, I don't know a lot. It's very much faster.
Okay. That's a good metric, yeah.
Yeah, I can't give you an exact number, but I can tell you it's very fast.
Okay. So, like, after he had done it and people saw the results, it's like, wow, this was definitely worth it.
Yes,
okay.
Absolutely.
Okay. Why is it so much faster than interpreting, like going through the AST versus just going from the Ruby code to the instruction sequences? Like, why is that faster?
It's actually kind of interesting. Ruby's compiler still has to produce an AST, and then it essentially takes that AST and then walks the AST and translates it into bytecode, which the virtual machine executes.
Right.
What's kind of funny is that Ruby 1.8, the interpreted version, had to do the same thing, except that it just stopped at the step where it came up with the tree. So you'd produce the AST, and then it would walk the AST and interpret it. Whereas it's kind of counterintuitive, but the compiled version with the virtual machine actually has to do more work. It has to produce the bytecode.
Right.
But you can actually, like, once it produces this bytecode, you can actually apply some optimizations to the bytecode. So you can do, like, some dead code analysis, peephole optimizations. There's different types of optimizations that you can apply to this style of code that you couldn't apply to just a tree. Right. And I think on top of that, there's also other things like, I don't know how big a factor this is, but a virtual machine executing bytecode is going to be more friendly for CPU caches than doing an AST interpreter, because you have, like, memory all over the place. So I'm not sure what percentage that plays into what percentage that factors into it, but it's there. So there's various different factors that make a virtual machine faster.
Just because, like, the nature of sequential instructions is kind of a very well-known problem, I guess, and people have come up with all sorts of ways to optimize
it. Yeah, absolutely. Yep.
Okay.
Yeah, so we can take those instructions and then apply known common optimizations for those to the Ruby code.
And then this virtual machine that we're referring to, I believe it's referred to as yet another Ruby VM. Right?
Yes.
Okay.
YARV. Yeah.
Right. Okay. And this was also written in C, right?
Yes.
Yeah.
Yes.
Okay. One thing I found sort of interesting is before I was actually doing research for this interview, I always thought of Ruby as an interpreted language, right? Like I always thought like, okay, you write your Ruby code and then the interpreter is reading your code, and as it reads the code, through the AST, things are executing on the machine.
Mm-hmm.
But this is more like, it seems a little bit more like Java, if I'm not wrong, where with Java, right, you write your Java code, you use a compiler to compile it down to Java bytecode, the .class file,
Yeah.
You run that in the VM.
Mm-hmm.
One thing I was wondering is, in Java, you compile down to the class code. In .NET, you compile down to, I believe it's called the Common Intermediate Language. So there's like they have their own sort of bytecode, I guess you could call it.
Yep.
But in Ruby, when you run a program, you just type Ruby space and you have like, your program, right? So why is there not like the same sort of bytecode compilation step?
It does have the bytecode compilation step. It does all the same steps, but it never generates the intermediary file. So it takes your program and it does convert it into bytecode. It's just that it keeps that bytecode in memory and then immediately executes it. So there's actually an interface where you can say compile a file and actually produce an intermediate file if you want to. It's just that people don't really do it.
Do you know if there's any specific reason why, like with Ruby, you don't tend to do that, but with other languages you do?
I think I would say it's because Ruby's origins are just a scripting language. You just run it, right? So nobody wanted to add that extra step. Like, you just want to run your code, right?
Yeah.
So I'd guess that's the reason.
And I guess like that isn't stopping like startup time or making it like too long or anything?
Well, that's an interesting question because it does slow startup time.
Okay.
Like, I think that's an interesting issue with this setup. So previously we were talking about Ruby 1.8 having to go through essentially the same steps as Ruby 1.9, but Ruby 1.9 has to do more because it's converting it to bytecode and then executing the bytecode, which means that the virtual machine has to be fast enough to make up for the extra work that it's doing.
Okay.
Right. So that parse and compile time, it is overhead that's being added to your program. So actually somebody made a gem called Bootsnap that what it does is you add this gem to your Rails application and it will compile all of your Ruby code into intermediate files like we were talking about. And then when you boot your application, rather than evaluating the text RB files, it'll actually load those binary files. And we found that it takes off maybe, what was it? I don't remember exactly. It's like 20% or something like that overhead.
Okay,
yeah.
So 20% reduction in the startup time.
Yes.
Okay.
Yes.
Okay, so that's something that's specific to Rails, though.
No. This is, you could use this, like they designed it such to be put in with a Rails application, but this technique you could use with any library that you wanted to.
Interesting. Yeah. So it's like, in a way, people didn't do it because it didn't seem like a problem.
Yeah.
And then I guess startup times, maybe specifically with Rails, were a little high.
Yeah. Typically, like a typical Rails application is going to have a way more code than, just some script that you're writing, right?
Right.
So in those cases where you have a large amount of code, that time does actually make a difference. So that's a case where you'd want to use it.
Cool. Yeah. So another thing I want to talk about is we've been talking about how you take the Ruby code, convert it to an AST, compile it down to what was the sort of bytecode called, or
There's no name.
There's no
for
name.
it.
Okay.
Just bytecode.
Okay.
Just bytecode. Yeah.
Yeah, so the
Ruby bytecode.
so the bytecode gets run by the VM.
Mm-hmm.
So this is a little different than like say C, right? Because C, you write your code and it actually compiles down to machine code.
Yeah.
Why would a language choose to compile to virtual machine instructions versus directly to machine code?
So usually you compile down to like this was the promise of the Java virtual machine is you would compile down to basically a common bytecode that you could run on any, like you could take it anywhere. So you take your class files, make your jar file, and you can run it on any machine as long as you have a Java VM.
Right.
So I think that's like the main. So I guess portability is one of the main selling points of compiling to bytecode, which Ruby's, I think. One of the things is that Ruby's the bytecode that I told you about that you can generate, it is not portable.
Oh, okay. So maybe not a real reason in Ruby's case, I guess.
Yes, that's not an actual reason in Ruby's case.
So the dream came real for Java.
Yes.
But okay.
Yes. Like for example, if you have it's the bytecode that you dump, if you dump it in Ruby on a little endian machine, it won't work on a big endian machine.
Oh, really?
Yes.
Interesting.
So it's not, the endianness is like, you can't do it. You got to run it on the same, if you're going to do that, you need to run it on the same architecture, which, we use this technique. Turns out in practice, it's like, fine. Like I'm not running, nobody is doing this. Nobody's running on nobody's developing on little endian and then pushing to a big endian in production.
Plus, I guess, like you said, the people typically don't do pre-compilation to, the bytecode and then copy it to another machine, right? So it doesn't actually end up being an issue, I guess, in that regard.
Yeah,
right?
in practice, it's not actually a problem. But we do, the main advantages of turning it into a bytecode for Ruby are essentially the optimizations.
Versus doing the interpretation.
Yes.
Right.
Yep.
Okay. But versus compilation to machine code.
Compilation to machine code, it's better. If you could compile completely to machine code, that might actually execute faster. But I guess the idea is that we have some things that are specific to our language that it would be nice if a chip implemented this instruction. That would be great, but we want to have more complex instructions than what a chip supports. The other thing is that in this case, our VM is a stack-based VM rather than a register-based one, which is different than machines. Actual machines actually work. So there's that issue too.
Can you kind of briefly explain what the difference is between a stack-based and a register-based?
Yeah, so the stack-based one, basically each instruction pushes and pops off of a stack. So you'd say for example, if you do the add, and if you want to add two numbers, you would push the two numbers onto a stack. So you'd have three instructions. You'd say push 1, push 2, and then you'd add, and then add would pop the 2 off and push the new value on. Similar to an HP calculator.
Okay.
Or an RPN, reverse Polish notation calculator. If anybody out there uses those, which I did in school. Whereas a register-based machine is where you'd say okay, I'm going to read and write from particular registers. So you'd say I'm going to put this number in one register, put this other number in a different register, and then I'm going to call the add instruction, which reads out of those and then puts the result into a different register.
So there is no concept of the stack.
Right. You're mutating registers rather than pushing and popping off of the stack.
Oh, okay. So you have to think about the actual position of everything.
Yeah.
Whereas with the stack, it's just going to kind of
grow and
shrink, and you don't have to worry about where on the machine that stack is stored.
Yep.
Okay.
So that's one difference, is that since Ruby's VM is a stack-based one, which is different from an actual machine, we can't do that step.
Okay. Interesting. Another thing I wanted to talk about is Ruby has, I believe, there's two separate APIs. There's a core API and a standard library. Mm-hmm. Is that right?
Yeah.
What's the distinction between the two?
The main distinction is that the core or the standard library, you have to require it. Like you have to specifically say like, I'm going to use this. Whereas the core stuff is just, you don't need to require anything. It's just immediately available.
Okay. So the standard, you have to manually add it in,
Yep.
even though it is shipped with...
It's shipped with Ruby. Yeah, it's shipped with Ruby, but you have to opt into those functions, basically.
Yeah. One thing I've also kind of wondered is how much of the core API and the standard library are written in Ruby and how much of it is C?
I'd say like core is probably 99% C. And the standard library is probably, I would say, I'm just estimating here, maybe like 80% Ruby.
Oh, wow. Okay.
So the standard library stuff is mostly just Ruby code that you can load and use, whereas the core stuff is just mainly C components.
Okay. And the core library, that would be like really foundational stuff like strings, dates, numbers.
Yeah.
Okay. And then things like, say, the JSON parser.
That would
be in the standard library.
Yeah.
Okay. And then so if somebody wanted to contribute to Ruby and they only knew Ruby, like, then it's actually possible for them to look at the standard library.
Yes, that's correct.
Okay,
Yep.
interesting. Very cool. You're on both the Ruby and the Rails core teams.
Yes.
Do you program more in C or more in Ruby when you're doing that kind of work?
It's a good question. Lately, I've been doing more C programming. It really just depends on what I need to work on at the time. Like lately, since I've been doing work on the garbage collector, that's all C code. Whereas like when I want to do here at RailsConf, I'm going to talk about improving the performance of templates, the template rendering system, and that's all Ruby. Yeah, the Rails views. I'm going to talk about that, and that's all Ruby code.
Oh, okay.
It just depends on which parts I'm touching.
Right.
Your code is powerful, and so are you. And when you consider the reach of your code, it's clear that to deliver quality code, you must also deliver secure code. Where can you start? A first step is educating yourself on basic secure coding principles and beginning to put these principles into practice every day. Vericode's Secure Coding Toolkit is your go-to resource for all your secure coding needs. The benefits of our toolkit include learning best practices for secure coding, understanding how to secure your DevOps environments, learning to combat the most common software vulnerabilities. Stay secure and download this valuable asset today at www.vericode.com/SERadio.
Next, I'd like to talk about something that I think when a lot of people think of Ruby and they think of performance, whether or not it's justified, they think of what's called the global interpreter lock.
Mm-hmm.
So both Ruby and Python, and I'm not sure if there's other languages, they have this global interpreter lock, this GIL.
Yeah.
Could you kind of define what that is?
Sure. In Ruby 1.8, it was a GIL, global interpreter lock. But now that we have a VM, it's a GVL, global VM lock. So basically, what it does is it ensures that only one thread is scheduled on the machine at a time.
Mm-hmm.
That's all it does. So it makes sure that only one thread can be scheduled on the machine at a time.
Okay, so you can have multiple threads,
yes,
but only one of them can be being run at any given time.
Yes, exactly.
Okay.
So what it means is that there's actually a lot of nuances here too, because it's possible to unlock that GVL. So you can say like, I want to execute outside of the GVL, but you have to do that in C. So let's say, for example, you have some kind of CPU-bound operation that you would like to execute in parallel. So, for example, maybe you're calculating let's say you're doing a Bitcoin SHA or something like that, and you have a library that's written in C, and that is CPU-bound. So what you would say is, in your C extension, you say, hey, I know this is CPU-bound. I'm going to unlock now, let it do its thing, and then relock. And then that way the VM can schedule other threads to execute on the CPU at the same time. And you can do the same thing for I/O operations as well. So as long as it's whatever operation that you're doing, as long as that operation doesn't need to call back into the Ruby virtual machine, you can unlock around that. A common example is that all the I/O operations in Ruby, so if you say like file.read or socket.write or whatever, those will unlock the GVL. and that'll allow you to do things in parallel. So you could say like you could create 1,000 threads and write to 1,000 sockets in parallel. Okay. So the GVL, this is why I say there's nuance to this thing. The GVL schedules one thread on the CPU at a time for pure Ruby code.
Just for Ruby code.
Yes. Okay. Yes. So anything that's written in C, you have the possibility to unlock it.
Mm-hmm. And you were just talking about how there are portions of, say, like the core API that are written in C. Is that considered like a part of that C code that can run in parallel? Or
yes.
Okay.
Yeah.
Okay.
Yeah. So we can say like in the C code, the implementation for the write function, it'll say like unlock. We know that this is an IO bound operation that does not need to call into the VM, so we'll unlock now, do the underlying write call, and then relock the VM. So during that time when you're actually writing to the socket or whatever, the VM can schedule another thread on the CPU to do something in parallel.
If I'm getting or I'm making web requests, for example, like I could make 100 at the same time, and because it's actually the C code that is doing that work, they can all run simultaneously.
In parallel. Yep.
Okay.
Yeah.
And then you were saying like if you wanted to run things in parallel yourself, that could be done through a C extension?
Yeah, you typically, if you want to run things truly in parallel, you have to do it through a C extension or use a C extension that knows how to unlock and relock the GVL correctly.
So you can have parallelism, just not using Ruby code.
Pure Ruby code, yes. So you cannot run pure Ruby code in parallel.
Got it. If you remove the GIL, what breaks?
Tons of stuff. One example of stuff that breaks is basically all data structures in Ruby are not thread safe. So you could unlock people have done this. You can just take it out if you want. If you don't schedule any threads, everything will work fine. But if you schedule a thread and like two of those threads mutate the same hash, then you'll get a segv or something. You'll just get a segmentation fault.
Okay.
So that's one benefit of this GVL, and that's the same in, I believe this is the same in Ruby and Python. Also JavaScript too. We don't have to have locks on those data structures because since only one thing can be scheduled at a time, you may get race conditions because it's concurrent.
Right.
But you don't get segvs because it's not parallel.
The data structures or the implementation of things in Ruby are not thread safe. Mm-hmm. And I guess that allows the implementation maybe to be simpler.
Yes.
And I guess you're saying it's also the same way with Python.
Yeah.
And so is that the reason why, like, say, JRuby is able to remove the GIL, I believe, right?
Yes.
And is that because they re-implemented all of the sort of core API things?
Yeah, so they implement theirs with, I don't think that their hash implementation, hash for example, but also array too. I don't think that those are thread safe, but on the JVM, you'll just get an error saying like, oh, you did a parallel update or whatever, right?
Okay.
But they do have thread safe data structures available to you too, because it's built on Java. Yeah. Yep. So
they actually have a separate class you could use, so you could have like a thread safe array or something.
I think so.
Okay.
I mean, I believe JRuby and MRI will have the same issue if you try to update one data structure in parallel. It's just that on JRuby you get a nice exception.
Yeah. Okay.
And on MRI you would get a segv.
Right. Which is not ideal.
No. It's not as fun. I would rather look at an exception than a segv. So.
Right. And so you're saying Python is probably the same class,
same
right?
Boat.
Same boat,
yeah.
And then I'm not an expert in JavaScript, but I believe you don't have manual control over threads.
Yeah, you don't have threads at all. Yeah.
Okay. So is it like
it's an implicit?
Yeah. So it's like they don't have a GIL or
no.
You
can do I/O operations in parallel, the same as on Ruby, right? You can do those things. You can do those things in parallel, but since they only schedule one CPU operation at a time, it's functionally the same thing as having a GVL.
There is no lock, but you just can't.
You can't. Yeah, you can't make a thread anyway. So
makes sense.
There's a few options for concurrency within Ruby, right?
Mm-hmm.
There's forking, right? So you can spawn a new process. There's multi-threading, but that has limitations due to the GIL.
Yeah.
And then I guess you have the ability to do an event loop, kind of like JavaScript or Node, right? When you're developing in Ruby, like how would a developer choose, I guess, what's the best model for them?
That is a good question too. It depends on the needs of your system, I think. At work, we use a forking model. And it seems to work, like that form of parallelism seems to work fine for us. But you could also you could just use a threading web server, for example. Like I think the default one with Rails now is Puma, which is a threading web server. And as long as your operations, like as long as your application is IO bound, you'll get great parallelism out of the threading server.
For example, you work at GitHub, right? So it's a lot of, I guess, web or HTTP traffic.
Honestly, I think a lot of our stuff is IO bound. Well, actually, that may not be true anymore. I think we have generating so it's kind of hard because like doing database stuff is clearly IO. Like you're waiting on IO, right?
Yeah.
But when you like actually generate the HTML to send back down to the client, that's going to be CPU
okay.
before you send it. And then when you send it, it's IO.
and that's primarily written in Ruby.
Yes. Yeah. So we use a forking model, but I mean, you can get great results out of a threading model too. It just depends on your application. Honestly, if I was a new developer, what I would do is just go with the defaults. I would just use Puma, put it into production, wait to see what kind of scaling issues I have, and then make my decision based off of that.
Okay, so probably start with threads.
Yep.
Okay.
Yep.
And then at GitHub, I believe you use Unicorn, right?
Yes.
Which is a web server that uses forks or additional processes for concurrency. So does that mean, let's say like 1,000 people hit the site, is it spawning a process for each hit, or like how is that?
No, we use a pre-forking model that forks. I don't remember how many processes, but it forks off like some number of processes. So we have essentially a fixed number of people that can be using our website concurrently. And if that gets full, then people are essentially put into a queue, and we drain that queue.
Just as an example, you spin up 50 processes and there's a queue in front of all those processes and it just passes it to each.
Yep.
Okay.
Yep.
Got it. When you use, say, JavaScript and you want to do something with concurrency, there's like concurrency primitives that are built in. Like, for example, there are the concept of promises, the async await keywords. In Java and .NET, they have their own sort of task or concurrency related libraries. Is that something that you think would ever come to Ruby, or?
It's kind of hard to say because like you could think of a thread as essentially a promise.
Sure. Okay.
Right. You could say like, I want you to execute this code and I don't care when you do it. I want to get the value at a later date. And then you would ask the thread, hey, are you done? And then when it's actually, there's a method on thread in Ruby, you can say .value, and that'll actually block. Like when you call it, it'll block until the thread finishes with whatever it's doing. So you could spin off a thread and let it do whatever. I'm not sure what the fundamental differences between that and a promise are, because both are just saying, I want you to compute this and I will get the value at a later date.
Yeah, I think and it may be certain things like being able to chain calls together.
Yeah.
For example, you can say in JavaScript, I want to run this HTTP call.
Then this one.
Depending on the result of that one, run this one.
Sure.
And it's sort of written in like a flat structure, so you can kind of.
Yeah, you could do it. So I think that Ruby has all the primitives to do something like that. Just if you want to have an API like that, you have to use a gem, for example.
Right.
We also have fibers, which you can think of as essentially coroutines. They're threads, but you have to implement your own scheduling model, basically. So there's that too. And then, of course, like Koichi's working on guilds, but that's different than promises. So it depends on what you want to accomplish. If you want to execute this thing for me, you can do it.
Right. And like you said, there are gems, there are packages where people have built sort of these concurrency, I guess, building blocks.
Yes.
So if you want to use promises or you want to use something like async await, like you can, it's just through a gem rather than being in the standard library or the core.
Yep.
You mentioned fibers. I wonder if you can talk a little bit about that, because at the Ruby conference, Ruby Kaigi, they were talking about a new web server called Falcon by Samuel Williams that uses fibers for concurrency. And I wasn't sure how that was different than using threads or processes.
Yeah, to be honest, I need to study how he's doing that exactly, or how that library is written exactly, because essentially all fibers are is they're coroutines. You say, like, you run a fiber, and inside the fiber you can say, hey, I want to switch off to something else now. It's truly, imagine that you had threads and you had to implement your own scheduler for the threads. That is what fibers are. It's like they're essentially a thread, but you need to say, like, hey, I want to pass off now. I want somebody else to handle, like, do something. So where threads, it's that scheduling's automatic.
By the operating system?
Yeah, by the operating system. Whereas these fibers, the scheduling is manual. You have to say, hey, go do this other thing now.
And so, like, you would be able to say, okay, go do this other thing, but you have to have some way of coming back to the fiber, right?
Yes. Yeah, you'd have to. So that other thing has to go back and say, like, hey, I'm done now. You go ahead.
Yeah. Okay.
So you have to manage that, and that's why I think it sounds like a pain.
Okay. Yeah, that's not something you want to think about if you're, like, building your app, right? It's like how to schedule
that stuff, exactly. Which is why I say I need to study how this web server works, because honestly, it sounds like a huge pain. And the other thing is that when you use threads with Ruby, as I was saying earlier, I/O operations will unlock the GVL, which gives the VM an opportunity to schedule other threads on the CPU.
Right.
Whereas if you're doing that with a fiber, fibers do not run in parallel, and the scheduler doesn't know.
Okay.
So you would have to say, like, I'm going to do an I/O operation. I'll switch fibers, or, like, I don't even know how it would work.
I guess what you're saying is, like, with fibers, I mean, you're doing the scheduling yourself, so you could have 10 sort of concurrent tasks where you're jumping between them, going, I'm going to do a little bit of this, a little bit of this. Yes. But they still can't run in parallel because they never drop down to C, I guess, or drop down into the Ruby runtime to say, like, hey, this is the...
You're never running a thread. Like, there's no thread. It's just there's no thread.
Oh, okay, yeah. So there's no thread, so you can't have parallelism.
Yeah, you can't have parallelism.
Oh, okay, got it.
So I say I need to study it, because I feel skeptical.
Right. Maybe you guys can have a conversation.
Yeah.
Next, I'd like to talk about the work being done to add a just-in-time compiler to Ruby. There's a lot of excitement around that lately. Do you expect a pretty big difference in performance?
It's hard to say right now. Like, if you run the JIT against CPU-bound programs, it works pretty well. Okay. Like, if you take one of the benchmarks that we use is we have an NES emulator.
Yeah.
And that's written in Ruby. And if you use the JIT with the NES emulator, you get really good results. Like, it's much faster.
Yeah.
But if you use the JIT with a Rails application, it actually slows down the Rails application.
Okay.
Although Kokobun, the person working on the JIT, he's giving a presentation here at RailsConf. So maybe he has some new numbers, but the last time I saw numbers, it actually made your Rails app slower.
Oh. Maybe not what they were going for.
No, I don't think that's what we're going for. But I do have pretty high hopes for it. So,
is there anything specific about Rails you think that makes it slow with the current implementation of the JIT?
I don't know for sure, but I would suspect that it's due to a lot of the. Well, first off, the number of method calls that we make. So this JIT is a method-based JIT. So you need to do some tweaking to say, like, how many methods you want cached or how many methods you want compiled. And Rails calls a lot of methods. Mm-hmm. And on top of that, Rails also has a lot of indirection. So I think those two factors may be inhibiting the JIT.
So when you refer to indirection, is that like a method calling a method calling a method?
Exactly.
Oh,
Yes,
okay.
yes.
Okay.
Yeah.
And so for a JIT, I guess it's better to have a, I guess, shorter stack.
Yeah.
Yeah.
Yeah, and I think, I mean, it may be fine, it may be okay. It's just that I really think it's the number of methods that are involved. Since we're calling so many methods, it's just bad. It's bad for the JIT essentially. And I think another thing is that I believe a lot of the meta programming that we do in Rails, some of the things that we do in there, I don't know what specifically, but some of the things we do in there will cause invalidations in the JIT.
So to give an example, like when you say invalidation, like the JIT is compiling like certain functions down to machine code, is that
Yes.
right? But then Rails does something to the function.
So, for example, let's say you had a simple method that was like, 1 + 2 or something, right? And that got jitted out to machine code, but then later on, say somebody adds the days method to the number class, right? Now the method tables are different. The shape of that type is different, and because of that, we have to invalidate this jitted method. So I don't know all of the things that would do that, but I'm also pretty confident that if there are things that do that, Rails does them.
Okay. Takes full advantage
Yes,
of meta programming.
Yes, exactly. It takes full advantage of those things that would mess it up. So.
The same thing you told people maybe don't do.
Yeah,
right?
maybe don't do that. Yes.
Very cool. Is there anything else you wanted to mention, or I think we should have talked about?
I don't know. We can talk about my GC work.
Okay. Yeah. That sounds good. Before we do that, let's maybe just quickly define what GC does and what its role is. Yeah.
Sure. So the GC is GC technology is very old. It was invented in the 70s with Lisp. And essentially what it does is manage memory for you. So you don't have to malloc and free things on your own. It's just managed by this thing called a garbage collector. It just takes care of that stuff for you, and you don't need to think about it.
Yeah. So basically, like, rather than in C, you would have to allocate memory, and you would have to free the memory when you're done with it. Otherwise, it would just continue to grow.
Yep.
Right.
Yeah.
GC sort of just takes care of that for you.
Takes care of that for you. Yep.
And I'm trying to think if we have time to sort of do a whirlwind tour of Ruby's GC journey, or we should just jump to your kind of current work.
I can give you an overview of what the technology that it currently uses. It's so like I said, I don't know how into the weeds we want to get here, but Ruby's garbage collector it's a concurrent garbage collector, so it runs concurrently with the program. It's a generational GC, so it's a generational mark and sweep garbage collector that has. I'm just throwing out all the buzzwords here, so people can look them up later.
Yeah. Well, we could maybe go a little bit into the mark and sweep, for example, right?
Yes.
That's like finding all the objects that are not being used,
or
being used, and then it's actually pausing the program, right? And then doing its work to figure out what's being used and then remove the things that aren't.
Yes, exactly.
And then you mentioned concurrent GC,
yes.
Right? So I guess that's just they're all happening at the same time, or
so what the GC does is we have so it's also a generational garbage collector, but it uses the 3-color algorithm. Look this up later. But basically what this algorithm allows you to, it uses tricolor marking is what it's called. It's called tricolor marking. And what this algorithm allows you to do is it allows you to pause in the middle of the marking step. So you don't need to yes, you have to stop the program to perform GC, but because you can do it incrementally, it means that you pause for a short amount of time and then you let the program continue. So you have more frequent pause times, but those pause times are shorter, and the overall throughput of your program is higher, essentially.
It's the same concept. It's marking objects and throwing them away, but it can do like a little bit at a time.
Yep.
So that your application has like a lot of quick pauses rather than long pauses.
Long pauses, yeah, exactly. So uses a tricolor marking technique so that it can do that. Right, so it's generational. It's generational too. So it looks at old objects less frequently than it looks at new objects, which also speeds up the GC.
So it can put them into categories. Like it can look at an object that is frequently being used, and it can say like, okay, I probably don't have to look at this one for a while because I've noticed it's getting used constantly. Is that...
It uses age. So when it was like, if some object comes to life and the GC runs, say, 3 times, and that object was able to survive 3 GCs, then it's like, we'll look at you like maybe we don't need to look at you so frequently, right? Then the other technique it uses is a thing called lazy sweeping, which is essentially a similar technique to the tricolor marking in that you don't need to halt the program. It sweeps objects away incrementally, so it'll pause and sweep and pause and sweep. So essentially the same idea is that you get short pause times and higher throughput.
Right. Okay.
And then the technique that I am working on is a compactor, which is basically for reducing heap fragmentation. So you'll end up with the garbage collector, like, because of the algorithms that it's using, you'll end up with essentially holes in your heap where you have, a place where there's no object anymore. And this compaction, the compactor that I have finished, and it's going to be in Ruby 2.7, it essentially allows you to get rid of the holes in the heap.
Okay. So it's like, as we're creating a bunch of objects, they're all getting like put into memory, but they're getting put like all over the place, right? Or... Well,
yeah, they're all put into a row, like you keep adding them to a list essentially, but let's say a GC occurs and some of those ones previously died and they went away, so now you get holes there. So you'll end up with these holes in it, and you can use a compactor to compress and get rid of those holes. And what that means is the benefits are essentially more efficient use of memory. It takes a while maybe to notice that you have all those holes and fill them in.
Mm-hmm.
So if we compact it, it can reduce, like, we put all these long-lived objects together. Maybe we don't need to look at those pages as frequently. We can use different techniques to basically speed up the GC and mutator with that.
It's kind of like going back to the generational concept where you were saying long-lived objects, right? You maybe don't need to look at.
Yeah.
And you can keep them all together like during this compacting process.
Yes.
Okay.
Yeah.
Very cool.
Yeah, so that's what I've been working on, and I am excited about it. That is what I'm excited about it because I wrote it. It took me like 3 years to write the stupid thing.
I think like what's great about that though is that when you work on something, it affects all Ruby applications, right?
Yes.
So you can work 3 years in this case, and if you get like, let's say, a 10% decrease in memory usage or something like that, that is across
it's
everyone's
app.
That's
everybody
huge.
That's using Ruby is like they're decreased. Yes. Yeah. It's cool.
Yeah. So that's fantastic. It's like more than just, I'm optimizing my app and I made it faster. That's cool. But like, you're like, I just made 2 million apps faster.
Yes. Yeah.
That's awesome.
One of the things that motivates me to work on stuff like that. Yeah. It's like, it's not just me and our app in particular. It's like everybody. Yeah. So
like, would you say the primary benefit with the compaction, is it speed? Is it reduced memory usage? Like, what's the main gain?
It's hard to say. It depends. So one of the things that we're looking at, so weird. You have to say, like, whenever you're looking at performance stuff, you always have to say, like, it depends.
Yeah. Developers love that answer.
Yeah. I mean, if someone doesn't say it depends, they're probably lying.
Yeah.
But so in this case, I mentioned before, we use a forking web server, and when you fork off children, the children share memory with the parent process, right? But one of the issues is that, I'll briefly explain the copy on write performance technique, is essentially like you fork off a child, the child process shares memory with the parent. It has, as far as the child is concerned, it has the same memory that the parent has, right? But that's not actually what's happening. What's happening is the operating system basically has a pointer back to the parent's memory.
Okay.
So if you have a program that consumes 4 megabytes, if you fork a child process, you don't suddenly have 8 megabytes. You still have 4, but you have 2 processes.
So you didn't actually gain any memory.
You didn't, yeah, you were able to get 2 processes, but you didn't double your memory usage. However, if the child process writes to the memory, clearly you don't want the parent process to be written to as well, right?
Right.
So what the operating system will do is it'll say, okay, if you're writing to this region of memory, I'm going to copy whatever memory was in the parent process. I'm going to actually copy that to you now.
Okay.
So the child process gets a copy of that. And that's the copy and write optimization is so that you can have 2 processes that don't consume twice the memory.
Oh, okay.
But when you write to that memory, you get a copy so that it's safe.
Oh, okay. So when you first fork a process, as long as you're only reading, it's actually reading the memory from the original process. So if I had like an object, like a string or something, and I read it from the second process, it would actually be reading the first process's string. But then as soon as I mutate it, then I get my own copy.
Yep, exactly.
Got it.
Yep. So they can maintain isolation from each other. So where this issue comes into play is that, so let's say you allocate a bunch of objects and then some of them get GC'd and now you've got these holes in your heap.
Mm-hmm.
You fork a child.
Yeah.
Now the child you're doing something innocuous, like you're allocating an object, but it gets allocated into an unused slot. And that's a write. Okay?
Okay.
So unfortunately, what that means is that the operating system, when it copies memory, it doesn't copy just the memory that you wrote to.
Okay.
It has to copy in fixed sizes.
Okay.
So on Linux, I think it's 4K.
Mm-hmm.
So even though you wrote this maybe tiny object, you'll end up getting 4K copied to your child process.
And you could possibly get like the object you wanted and then like pieces of whatever is left.
Yeah, exactly. So my idea here is that if we compact the heap before forking, there will be no spaces for you to allocate any objects into. So now the child process, when it allocates a new object, it'll allocate it off into an empty location, something that's not shared. Right. The issue is that eventually, if you have holes everywhere, eventually all of it's going to be copied to the child process. Whereas if we don't have any holes, then none of it will be copied to the child process.
Interesting. Very cool.
So that's one thing. And there's some other optimizations. Like it's possible it could increase performance, but with the particular algorithm that I implemented, it's unlikely. There's other compaction algorithms that I plan that would be better for performance. And I plan to implement those later, but not now.
Okay. You got enough on your plate, right?
Well, the thing is, like, so for a very long time, people kept saying that writing a compactor for Ruby or for MRI was not possible. Like, you just couldn't do it. But I figured out a way to do it, and the way that I do it is independent of the actual compaction algorithm.
Okay.
So what it means is I just chose like the easiest compaction algorithm because that's not really the problem I was trying to solve. Right? Yeah. I was trying to solve like, is this actually possible?
Right.
And then once we figure out, oh yeah, it is possible, we can do this. Now I'll implement a more efficient and more performance friendly technique.
What was the specific part of Ruby that people said like it couldn't be done?
So the main issue is C extensions. Mm-hmm. So if you allocate, like let's say I allocate an object in Ruby and I pass that object to a C extension. The C extension gets the address of that object, and it's a direct address. So if that C extension were to save the address somewhere, and then the compactor ran and that object got moved, then the address is wrong.
Right, and the C side would segfault when it tries to...
Exactly,
Yeah, okay.
yes.
Okay.
So What I did was essentially I piggybacked off of the mark function. So if you have a C extension and you have a reference to a Ruby object, you're supposed to implement mark and sweep functions, and you're supposed to mark that pointer. So what I did is I said, okay, any object that gets marked, we don't allow it to move.
Okay.
So internally, Ruby uses a different marking function than C extensions use.
Oh, interesting.
So that was also part of the work that I had to do, is say like, okay, what we're going to do is we're going to take this public API that everybody uses.
Yeah.
We'll ensure that those objects do not move. Ruby's internal one, we're going to do something completely different because we know what to do. We can handle the situation.
Right.
So that was essentially the technique I came up with. And after doing that, what it means is that certain objects can't move, but it also means safety for your C extensions.
So that means that when it comes to C extensions, does that mean there will always be like holes, I guess, in terms of the compaction?
No, not necessarily, because the way Ruby's GC works, or the way its allocator works, is it allocates a page. It's essentially an arena, and a memory arena of each page is about 16K, I think. Basically, we allocate objects out of that arena, and then your heap is composed of multiple pages. So obviously, you probably want your program to use more than 16K.
Sure, but that's more than enough for anyone, right?
Yeah, that's more than enough for anyone. So we have multiple pages, but what I did is I said I take those pages and the compactor sorts them by the number of unmovable objects they have.
Okay.
So then we just pack around all of those unmovable objects.
Okay.
So even though we have some that can't move, we can still make sure that everything is solid.
Yeah. Interesting. Okay.
So it seems to work well. And then I also introduced a compaction callback for C extensions. So let's say you have a C extension and you want to support the compactor. You can register a callback that'll say like, every time the compactor runs, this callback will get called, and your C extension has an opportunity to update its own references.
Okay.
So there's another function that you can call and say, hey, here's a reference I have. Is this right?
Mm-hmm.
And then the GC will tell you, oh, yes, that's fine, or no, it's actually now in this location. You need to update it.
So if you have control over the C code, then you can actually you can say like, I want to allocate this memory, and if you move it,
let me know. Yeah.
And then so my pointer will still continue to point at the right location even if it got moved.
Yes.
Awesome.
Yeah. Yeah. So that's I'm excited about it.
Yeah. No, that's cool. And I'm learning a lot too. Like, yeah, it's like when you program in a high level language like Ruby or Python or even Java, like it's like you don't really think about what's happening under the hood, and it's just awesome how much goes into it.
Yeah, I think that's really good though. Like I think most programmers shouldn't really have to think about that type of stuff. Like really, you just want to be like, you want to be writing your app or whatever problem it is that you're trying to solve. Yeah. So I think it's actually cool that we have abstractions like that you don't have to bother with.
Yeah. Awesome. Well, I'm glad you're on the case.
Thank you.
Is there anything else that you want to mention, or?
I can't think of anything else. No. I mean, JIT's super exciting. Just, I think Ruby's future is very bright. So on the heels of RubyKaigi, seeing all the awesome announcements at that conference, like, I'm really excited.
Yeah, I mean, it seems like, and maybe it's not a correct perception, but it seemed like Ruby as a language, it didn't seem like there was a lot of big changes happening, at least from the outside. And then it seems like there are a ton of things that are coming all at once. Does that sort of sound?
I think so. Yeah, that sounds truthy to me. I mean, I don't think there are huge like language level changes, but I think that the underlying technology and the new developments and stuff, like new libraries and stuff that are coming out, it's just like, I feel like there is a new life, I guess. It's just like, I think right now is a very exciting time.
Very cool. What are some good resources for someone who wants to learn more about the Ruby runtime or learn more about the work you're doing?
I would suggest a book called Ruby Under a Microscope. That book is very good about Ruby internals. It teaches, like, it covers Ruby internals really well.
Yeah.
So I recommend that book. For the stuff I'm doing, me in particular, I really enjoy a book called GC Handbook. I actually stole like all of my everything from there. Basically, I read the book and I was like, huh, that's a good idea. Yeah. Maybe I'll do that.
Yeah, that's software development, right? You read someo's paper or someone's,
You're like, oh, that's a good idea. Yeah. I'll do that.
Genius, right?
Yes, exactly.
Nice.
So I recommend, like, if you're interested in GC topics, I recommend that one. Compiler books, I don't know. There's a lot of compiler books out there. I mean, but the best one I think the best book that's specific to Ruby internals would be the Ruby Under a Microscope for sure.
Yeah, I had a chance to kind of go through it, and it's really fantastic.
Yeah, it's great. It's in depth. It's how old is that book now? Maybe 3 years.
Yeah, I think it got reprinted or something through No Starch. Like maybe 2014. I don't know.
I mean, obviously, like, books age.
Mm-hmm. Yeah.
But it's still, I would say that it's like very accurate still.
For sure. Finally, how can people follow you?
You can follow me. My nickname is Tenderlove. You can find me on Twitter with that name, and also on my GitHub with that name, and also on my Instagram with that name. I don't have a SoundCloud, though.
But it's coming.
It's coming, yes. Don't forget to like, follow, and subscribe.
Absolutely. All right. Aaron, thank you so much for coming on the show.
Oh, thank you so much. It's been a pleasure.
This is Jeremy Jung for Software Engineering Radio. Thank you for listening.
Thanks.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.